Well, it's more what I didn't see. What did I not see, KJ, in your lab journal? Huh?
Graphs.
Graphs.
At all?
Yeah, that's right. You did no graphs for me. Lazy son of a gun.
Like for even the written, the typed one?
No, for his handwritten ones.
Oh.
Breaks my heart. Breaks my heart.
You want to see the last bit?
Yeah.
Right, next now. Write this down, please.
I did the graph like last morning.
Look, KJ has his own way of doing things. Some people might say it's the wrong way to do things. I just prefer to think of it as a different way to do things.
Some people say it's wrong to do things.
Yeah.
Oh no, my pen is not working.
Alright, you got this?
No. Pen is working.
Well, we have to start.
Electric field transformer, electrical
Yeah.
structure.
Okay. Right, so, well, there should be breaks there. Oh well. So anyway, different charges configured in different ways will produce different electric fields. And we'll look at 4 types which you can get in the exam. So the 4 types are, which you should note, a point, a sphere, parallel plates and a dipole. Now we'll see the graphs in a moment, but I want you to write the 4 names of the possible configurations you could have.
Types of electric field.
Well, yeah, more like electric field configurations. Yeah? So you'll get the names again anyways, because I'm going to give the names in the picture. So the first one is a point charge. Yeah? Yeah? Okay. So the first one is a point. What's taking so long? I just need you to write these 4 points down. Yeah?
Yeah.
Alright, I'm continuing. So the first one is a point charge. So if you have a positive charge, the electric field is going outwards, and if you have a negative charge, the electric field is going inwards. So this is the simplest one, and it's not surprising, because if you have a positive charge, will it be pushed or pulled? Pushed away or pulled towards here? If I put a positive charge here,
Yeah.
it should be pushed away. So the arrows go out. And if I put a positive charge here, pull towards. Yeah. So please draw these. It is a common enough question in the exam to ask you to draw one of these configurations. So this is the first one, the positive point or the negative point electric field. Do you draw both? Show me these beautiful drawings. Let me see. Still do. Next. So what's the next one? Yeah. I don't know why they bothered to ask you to do this one. It's basically the same as the point. So a sphere, it's the same thing. Like if you have a lot of positive points together, there'll be an outward field. And if there was a lot of negative points, inward. So draw it anyways. It's basically the same thing. Okay? Correct, you draw the first 2. Look, this isn't a movie, okay? You're not watching something here. So I want these to be drawn because you could be asked to draw them in the exam, and then I want this one to be drawn. Draw. Yeah.
Both
Huh?
plus and positive and minus.
Yeah, yeah. That's great. Okay. I just want to fix something here so I don't forget. Alright, the next one. The parallel plates, I think, is next, is it?
Yep.
So parallel plates. So what I mean by parallel plates is you have an electric plate, electrically charged plate, an electrically charged plate. It'll make a field between the two plates. So if you have the positive charge on the top and the negative charge on the bottom, you get this field that goes basically straight down. But please note, it is a little bit curved at the ends, but it's essentially straight down.
Keep in minus plates or open or straightforward.
Yeah, if they're swapped, yeah. Got this? Yeah? And what's the last type?
Electric dipole.
Dipole. Now, use your English. There's a prefix in the front of dipole. What's the prefix? Di.
Two.
Di means two, and pole?
Pole.
Cool.
Yeah, like a pole. Yeah. So a dipole is when you have a positive and a negative lined up, you know, like this or like this. So here's the diagram. In fact, you've seen it already. This is the dipole. This is the one I showed you last time. So the field goes from positive to negative.
We have to draw it again.
Yes, please. So they're all together. Look, all I'm asking you to do is draw pictures. Come on. Yeah. Continue.
Yes.
Okay. So for the exam purposes, these are the four possible electric fields that you could be asked to draw. Yes?
In the parallel plate, does it matter how many poles the line will have?
No, no, just get the general idea. Right, equipotential refers to the part of space where every point has the same potential energy. So equi means equal, so it's the point where all the potential energy is the same. Now, we'll have a look at that in a second, but please grab the definition here. Sorry, I screwed up my English sentence there. It should, of course, be good English, not bad. Equipotential refers to do I want to make it there or the region in space where every point in it has the same potential energy. Alright, that's it there. Don't write pause, okay? Refers to the region in space where every point in it has the same potential energy. I don't want to say would have. It doesn't matter. I'm thinking too much. Okay, so I'll draw what I mean here. Can I just flip to the pad for a moment? So, if we think about potential energy due to gravity, this person here has the same potential energy as this person. True?
Yes.
Why?
Because they're standing on the same level.
Yeah, and this person here would have the same as this person.
Yeah.
And this one here would have the same as this one here. So if you were to draw lines, everybody here has the same potential energy. Everybody here has the same potential energy. Everybody on this line has the same potential energy. These are the equipotentials. The lines, if you're anywhere on this line, you have the same potential energy. And if you're anywhere on this line, you have the same potential energy, and so on. This is for gravity, just equipotential. So what we're going to do is we're going to have a look at the equipotentials for the electric field. So there's only really three to look at. The first one is if you have a point. One thing about equipotentials, for the electric field, you kind of have the same idea that if you are here, you have the same potential energy as somebody who is here, the same distance away. A bit like the gravity. And if you're here, you have the same. So basically, if you're anywhere here, you have the same potential energy everywhere. Because you're the same distance from the electric field. Yeah. So, the equipotentials would look like this. Yeah, like the electron. Like each electron, if you've done this in chemistry, each electron shell has the same energy, potential energy. Have you done this in chemistry?
Yeah, different level chemistry.
Yeah, have you done this in chemistry? It's yes or no?
Yeah.
Yes. So have you learned in chemistry that there's different energy levels of electrons? Yeah. So at anywhere in that level, as long as it's the same level, it's the same energy. So in fact it's the same idea, equipotentials, okay? So everywhere here on the same line is the same potential energy.
So at that time the energy gets less or more?
We'll talk about that later. Yeah. That's a different lesson. But to answer your question, the potential energy is increasing.
Yeah,
as you move out. Yeah. But this is something we'll do in chemistry and something we'll do as well in physics. Can you draw this? Because in the exam, what they usually ask you to draw is the electric field and the equipotentials.
This is the first one.
Well, it's the first two, really. Yeah? Okay. The next one, the parallel plates. Now, again, you're not going to be too surprised to learn that the equipotentials will look like this. I mean, yeah. Well, they are supposed to be parallel, yes.
I mean like they're upside down, horizontal.
The horizontals.
So vertical.
The vertical's the field.
Yeah.
Yeah.
It's
basically the distance from the plate. Also, Fahad, think about it as like, the gravity one as well. The horizontal lines. It's just like the picture I drew with the gravity one.
The last one, even the curve one is.
Now, if you want to be technical, they curve a little bit at the end. But I'm not going to worry about that in the exam. Okay, and the last type is a little bit difficult to draw. You have your positive and you have your negative. So remember, the field, you know, goes like this, doesn't it? Can't remember. And then there's then it goes outwards here. This is just the electric field, and then it goes inwards here. Okay, so now time to draw the equipotentials. So if I'm here, does anyone have any idea where I would have to be so that there's the same potential energy? Now, I don't expect you to know, but I'll give you a little hint.
On an algebra triangle.
No, wait one sec. I'll give you a little hint. Places where the potential is the same is also where the force is the same. So think about it like this. Where would I need to draw this point so that it's still the same force on the point?
Inside.
Well, how much force is on this point right now? Zero, basically. So where else would I have to draw it? It's not going to be here, because if I put it here, it will move towards the positive. So it's not a zero force. So where else would I have to draw it? Yeah. All the points here have no force, so all of these have the same potential. Now look, when I'm very close to the positive, I need people listening for this. When I'm very close to the positive, I can forget about the negative because it's far away. So the equipotentials near the positive would look the same as the first diagram I did. They would be circles. Likewise, they would be circles here. But the question is, what happens in this part of space where I go from here to here? Well, here there's circles, true? Here there's circles and here's a line. So as I move from here to here, the equipotentials change from circles to lines. So they kind of get distorted to become lines. So it's trying to draw this is a pain in the backside, but you get the idea that the circles start to morph into lines. Now, for the exam, I think if you just drew this, something like that would keep me happy in the exam. Well, maybe not as ugly as that. But it shows me that you've got the idea. So, you've done energy levels with Lorraine. So this one here, this is like the zero energy level. There's no energy here. This one here is like the first energy level and so on. Anyways, please draw nicely. Beautify. Where's Yemi?
Not in my pocket.
Nobody knows? Huh?
What do you call these three graphs?
Equipotential graphs.
For each one there's a name or?
Equipotential for the dipole, equipotential for the parallel plate, equipotential for the point. Continue?
What about the first one?
Which one?
The
The point and the sphere are the same.
It looks like some animal's eyes.
Huh?
Some animals, like.
an owl.
Yeah. Alright, continue.
Yes.
That shouldn't say plates. No, it should. Okay, so the third configuration we did was the parallel plates.
Yep.
Now you have a formula to work out the electric field strength. What's the formula for the electric field strength? F over Q. The big problem with that formula is that you need to know what the F is. That can be very difficult to figure out. There is another way to calculate the electric field strength if you have parallel plates. So if you have one plate here and one plate here, and this is a positive and this is a negative, and it's there's a battery running between the plates, the cell here. So this cell makes the electric field between the plates. If you know the voltage of the battery and if you know the distance between the plates, you can know how strong the field will be. When a current is passed through two conducting plates, separate the distance d at a potential voltage, a potential difference V, then the electric field has strength V over D. So if you know the voltage and if you know the distance, you can know the strength between the strength of the electric field by using this formula. Electric field strength is voltage over separation distance.
Alright, spell it down.
The formula is enough here. But you might want to write down what the V and the D represent.
Okay.
So, when a current is passed through two conducting plates separated distance d at potential V, then an electric field is produced. Oh no, the English I guess is okay.
Are we going to use this formula?
Oh yes. Yeah? Got that nearly? Okay. So this is interesting because it means that if you bring the plates closer together, does the field get stronger or weaker?
Weaker.
Now think for a moment before you answer.
Very stronger.
Yeah, so if you bring the plates closer together, the distance gets smaller and the electric field strength will get bigger.
Can you go to that picture you draw?
Which picture? My happy picture?
Yeah.
Really?
I need to come with.
Ah, no.
This one.
Oh, this one, yeah.
What's this?
Yeah, you should draw this too, because it's the situation that we have. So it's very easy to make an electric field. You can do it at home. You just need two copper plates, put them close together, but don't touch, and then have a battery connected to the plate. One part connected to the positive, and the bottom plate connected to the negative, and then you've got an electric field. Now, if you could put it in a vacuum, that would be better, but it still would work not in a vacuum. So your goal is get them close but not touching. Makes the field stronger.
You can hold it.
What will you do with the electric? How you know it's there?
Yes, we'll see what you can do with electric fields later, but there's a relationship between electric fields and magnets, so then if you had a compass you can start doing things as well. Yeah, we'll do all of this stuff. In fact, there's an electric field in your old-fashioned television. You know the big televisions?
Yes.
The big box.
Yes.
The ones you have. That box part at the back,
Yes.
there are 4 plates in that. 2 horizontal and 2 vertical plates. There's an electric field produced between the plates. The field.
The whole thing.
The big part. The reason that old TVs are so big is because that big box at the back, there's a big electric field there.
I'm saying that the whole thing, the end part is called cathode ray.
Oh yes. Cathode ray tube. Yeah. Okay. Continue.
Yeah.
Yeah. Okay.
Which cannot be connected to HDMI.
Yeah.
Oh, no, definitely not. Okay,
Why not?
so that's the plate. So we need a formula for the strength when we have a point or a sphere. So a charge Q will produce an electric field of strength. So here's the formula. Let me draw it here. So if we have a charge Q here, it will produce an electric field, and the strength at a distance r.
It doesn't matter if positive or not.
Well, it does, but it only matters so far as it will either push or pull. The strength number will be the same. Is this? This is the formula.
E is equal to
Yeah, electric field strength
That's
is
zero.
1 over 4 pi epsilon 0. I'll explain what that is in a moment. Q over r squared.
Maybe you're right.
It's epsilon 0. Yeah?
You'll be happy with your.
Well, no, you wouldn't. Divided by 0 wouldn't make you happy.
You did have picture. They draw.
Huh?
This thing.
Oh, it's not even that's not a picture, that's a nothing. Okay. Next. Now,
is it 1 or I?
1.
Can't see.
Okay. Now, I didn't tell you in this definition, I should have. Epsilon is just a constant. We don't study what exactly it means and what it's used for in this course. So for you, it's just a constant like the G constant or any other constant in physics. So it's actually on your calculator, but I'll give you the value here. Epsilon 0 is 8.85 times 10 to the minus 12. And we can work out the units, because the formula is E equals 1 over 4 pi epsilon 0 Q over r squared. So you have epsilon 0 equals 1 over E 1 over 4 pi Q over r squared. So what's the units for E? Newtons per coulomb. So what's the units for 1 over E? Coulombs per Newton. This doesn't have any units. What's the units for Q? Coulombs. And the units for the distance? Meters. So this will be meters to the minus 2. So the unit here is coulombs squared per Newton per meter squared is the unit. Now this value is on your calculator. It's constant number 32 on the calculator. Okay? Yep. I have 2 examples to do and then we'll finish. Okay, so the first example do you know what? We have maths later today, don't we?
Yeah.
So do you know what? I'll break this lesson into 2 parts. I'll just finish these examples in the maths class at the start, and then we'll do the maths, okay? Because I have to get ready for the mid-semester test for the January students. Remember?
You don't have.
Yes.
No maths. So look, I'll do these 2 examples at the start of the maths class after lunch.